to come in of blah 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 from me. First of all, a couple of details which are simple is just to let you know that the intervention, the presentation today will be recorded because it has been accepted to be recorded. So if you have colleagues who do not have the chance to attend this event and they want to see outside, afterwards the presentation, they can go through the event thumbnail, through the URL, access the video that out of this event. Now, for me it is a pleasure to host today Dr. Dave Probert from Microsoft. Just a little bit of background before I give the word to him, which is the interesting part, of course, is that he is like we have nowadays the fashion of the hybrid technology. He is a real hybrid developer and hybrid intellectual, in the sense that he has been working intensively both in the UNIX world and in the Windows world. Now he is a kernel developer, is one of the kernel developers at Microsoft in the Windows core operating systems, yeah, at Microsoft. He has been at Microsoft for 13 years now, since 1996. He has a Ph.D. in computer science and engineering, computing engineering, excuse me, from Santa Barbara. And for me, what is particularly special of this event is that we are going to have today the possibility to put in contrast the Windows technology compared to the Windows technology concerning the kernel development compared to UNIX. So we will have some report on the recent changes to the kernel, to the Windows kernel, and in particular some emphasis on the differences to UNIX, to the current UNIX. So I think that it is a very interesting event. I can see from the attendance that it has been so appreciated. And I don't want to say longer because there are no more people coming through the door, so I want to give the word to you, which is a pleasure. And by the way, I suggest, except for short questions, I suggest that the longer questions, so the debate, is moved to the end of the presentation. So just we let him essentially going through the presentation before going to interruptions. Huh?
Or argue with me anyway. It's okay too. Thank you very much for that introduction. I was realized coming to Europe to do. Sorry? Well, I thought it was loud before. Okay. I know it's coming to Europe. I have to speak at a computer science education conference as part of a vendor thing. We're supporting this conference in Paris. And I said, gee, I'd like to go see Switzerland again. I love Switzerland. And then one of my colleagues says, would you like to go talk at CERN? We can get you invited to come give a seminar. And I got to say that this has been the thing I've been looking forward to most, was this visit today. So I've enjoyed this very much. Had a great tour. And I understand you guys, there's CERN the movie now, so I'm going to go see that, which I hadn't bothered to see it yet, so Angels and Demons, so I'll go take a look at that. So thank you very much. I'm going to talk about all the things that you heard about, and we can sort of change the proportion of some of them as you have questions. I have to give it focus. Okay, so having come from a background that really I spent most of my career in UNIX, the way things started out for me is back in the 70s, the really cool new computer. Anybody have an idea what the cool new computer was at the end of the 70s? It was the VAX. It was the digital VAX 11780 that came out. It was like a 32-bit mini computer. It had virtual memory, you know, all the kinds of stuff you read about when you heard about Multics. Anybody know what Multics is? Okay, so I actually go back far too many generations, I guess, but that's okay. You guys know what Unix is, though, right? So there's a really terrible joke about the relationship of Unix to Multics, which if you don't know, well, that's what the internet is for. You can go find out what that joke is. So Unix was the thing that came out of the ashes of Multics in '69. And I did some hardware stuff, and this guy at the university, who I'd taken a class from, said he was going to get a VAX because we were starting a computer science department in Santa Barbara, and he says, if certain things happen a certain way, would you come manage this VAX in the university? And at that point in time, I was a hardware engineer designing hardware for Burroughs, And I said, yeah, that's like the coolest machine ever. You get that machine and I'll do it. And so I went to the dark side and I became more involved in operating systems than I was in hardware pretty much from that point of my career on. Although I did spend some time working on many supercomputers, as we used to call them. I worked for Glenn Culler, and then I got to do a tiny bit of hardware design, but mostly operating system design. And so all that world, I was like in the UNIX world, and then I came to Microsoft, and first thing that happens when you get to Microsoft is, can I ask a question about the audio? Is it possible to turn it down a little? Can you hear me in the back? If you can't hear me, raise your hand. You can hear me fine, right? I get in this really terrible echo. I feel like I'm in the middle of a tin can. Well, I will deal somewhere. It's like hearing your own voice. You never played like a tape recording back and it just doesn't sound like you. That's what this is right now. It's very strange. And you get to Microsoft, and everybody you knew in the university sent you every terrible Microsoft joke they ever came across, you know. And so I got a lot of that, and I kind of had to make this transition. And then I got involved with universities because I started giving out, even though I was working in the kernel team, I started giving out source code to the kernel to universities so people could teach it in operating system classes, because that's how I learned operating systems, was reading the UNIX version 6 source code back in the late 70s. And I needed to, for myself, kind of rationalize the difference between these operating systems. Have any of you ever considered that there's kind of a religious kind of war debate that takes place between operating systems? Right? I mean, who here is with Unix? Who's on the Unix side? Come on, be honest. All right? And who's on the Windows side? Okay? And who of you think that your own operating system you're going to write someday will be the winner above all? Okay. So that's what I did when I was working on my Ph.D. And the resolution for this operating system war thing finally occurred to me that operating systems are designed as engineering solutions to a set of problems. And the design decisions, the fundamental design decisions that get made inside operating systems are driven by the circumstances, the environment in which those operating systems are designed. And the world seems a lot more rational if you take this point of view. So if you go back to 1969, when Unix was really, I guess, fully conceived, or the initial conceptions of Unix at least had started, this is a world of 16-bit program address spaces, you know, a few kilobytes of memory. These are swapping systems. There's no virtual memory hardware. These are the mini computer-like things that you could afford in laboratories back at Bell Labs. They happen to have one sitting around. I just realized I control my own destiny. Let's see. Do you still hear me? Okay. Gosh, I forgot where the fundamental volume control was. So a lot of characteristics. The user environments back then were very different too. So what was the security model for Unix based on? How many of you run SE Linux? Anybody? Good. So we won't talk about SE Linux. So if you look at Unix and Linux, what's the security model? The world's divided into 3 categories, right? Me, my friends, my people in my group, and everybody else. That's like the world. And then you get up to 20 years later when NT was designed, and the world was a far more complicated place, right? You had the idea of a whole bunch of different sets of people with different kinds of relationships with security, and security technology, the software technology advanced. And so it's a very large, diverse user population that you're looking at versus like a small number of friendly users in Unix. The whole nature of threading. Well, let's look at the sort of how some of these decisions go. The nature of concurrency. What's the unit of concurrency in Unix? It's the process. Even when you're trying to make them threads in Linux, you do it by saying, oh, it's a process, but it's a process that happens to share the exact same address space as this other process. People have added threading to Unix over the years. What fundamentally changed is that we got multiprocessors. Those machines we originally had in like 1969 and through the 70s, up into the 80s actually, that you could afford, were single processor machines. And even though there were a lot of people trying to figure out how to accelerate scientific code, beginning in the 70s, parallel computing, Probert and Hansen's work, concurrent Pascal, it all started at least in the universities in the 70s. It wasn't until the 80s that we really started looking for how you could accelerate single programs across multiple processors. And you get into that model, and then all of a sudden threads start to appear. So if you just take a look at operating system design away from the religious kinds of connotations of this is the way to do it, you start to see there's a lot of engineering that took place based on the environments. One of the things I kind of love to pick on is fork. Anybody not know what fork is? Fork is how you create a process in Unix. It's a really stupid idea, to be honest. It's a terribly stupid idea. And I won't go through the whole argument with you. I always win this one. I think it's because I can move the microphone up higher or something, but I tend to win this one. But it was a brilliant idea back when Unix was conceived. But it's really kind of a terrible idea for creating a process today, because if all you're really trying to do is decide what 0, 1, and 2 are, you could add 3 extra parameters to exec. It's not like we've been shy about adding parameters to exec over the years to actually get 0, 1, and 2 to be what you want. But why do you think it was even though it might be a terrible idea, and I'll tell you the thing, I usually win the argument because after you go through all the changings in virtual memory sizes and how much you have to copy and how large the page tables are and what happens if the page tables are actually paged, which they might be in an operating system other than Unix, you end up in the problem of threads. In a multi-threaded process, that fork doesn't actually make a real lot of sense. What do you do with all the other stacks, all the other activities, if all you're really trying to do is like create this copy so you can exec a program? Why not just exec the program? But back at the beginning of Unix, these were low memory swapping systems. And the way in version 6 and version 7 Unix fork was implemented is that you swapped the parent process out to disk and you gave its memory to the child. In other words, it was really a pretty brilliant kind of idea. You know, it was driven by the engineering, an engineering solution to the actual problem space that they had. And it's actually a really very cool idea. When I go to universities and I ask students this, I usually get very little understanding into why you might build something one way versus another. And I think that's really important. So what operating systems really should come down to is saying, well, what are the right kinds of ideas? What kind of ideas meet the problems that we have? What's the best kind of engineering, and move off the religious war kind of thing? And there's a real good reason for this, which is, if you pay attention to that last environment slide, you know, 16, 32-bit, but the world's changed radically. And just looking at it a few years even, it's going to change radically more. Whereas multiprocessors gave rise to multi-threading as being very important. I think it's very likely that this coming mini-core thing that Intel and AMD are talking about will give rise to the task. Think of a task as a small subdivision of work, not the Linux task or the Mach task. With small pieces of work that then get mapped onto threads to get access to the CPU, this may become a dominant model. So in our parallel computation environment, this thing called ConcRT that we put into Dev Studio 2010, you can download the beta, you can play with ConcRT. It thinks, it uses some technology out of the universities called Silk, C-I-L-K, if you've ever read those papers. It says that what you want to do is you want to over-decompose your problem into lots of little tasks, and then you want to use queues that allow you to do load balancing between the available number of CPUs, including dynamically change the number of CPUs. But you want to think in terms of these tasks, you don't want to think in terms of threads. We've actually been doing this kind of thing for a long time with things like thread pools and servers, where you actually end up thinking about your program in terms of a set of tasks. Somebody comes in to some port, they say, please go do this service for me, please go do this SQL query, please go serve this web page, and you end up saying, oh, let me take a task designed to accomplish that request, and let me go multiplex it onto threads using some kind of thread pool environment. So already the environment's changing, and once we get to mini-core, we start to have dozens of cores on clients, it's very likely that threading models will change yet again. And there are a lot of other things that are coming along. The curse of performance has been for a long time seeks, the electromechanical seeks. And SSDs are starting to show a lot of promise. And if nothing else, solid-state disk is going to represent another important level in the memory storage hierarchy. So the interesting question is not, will Windows run in these environments? Because Windows does. Will Unix or Linux run in these environments? No, of course it will. The interesting question, and this is from an operating system research point of view, is if you started over like you did in 69 and 89 and 2009, you started over with kind of a blank piece of paper, you know, the knowledge of what's come before, but a blank piece of paper, what kind of system would you design for a core operating system going forward? And I got to tell you, it's Windows 7. No, I'm just kidding. I was at ETH, and this guy, I didn't know who he was. It turns out he works at University of Washington. I really admire his work. Was in the audience, and he kind of jumps ahead, and he's kind of saying, you're about to say that Windows 7 is like this. And it's like, no, I'm not. I'm saying that we have a lot of interesting work to do in operating systems. It's a field I love. There's a lot of great stuff to do. Not a lot of people doing operating systems work anymore. I think I'll probably find more interesting operating system stuff happening here than most of the other places in the world. I mean, how many of you are at CERN because you want to start a web company and go make, you know, tens of millions of dollars? No, okay. But most of the places that go, like in universities, I mean, that is the ambition of everybody who's entering computer science these days. So we have lots of challenges. The scale of computing has changed, the scale of address spaces, the scale of memory, the scale of storage, new hierarchies. Hypervisors have become important. We're way behind the curve on this. Our security models are completely obsolete because the models behind security were all based on how you share a computer system, right? And what that really comes down to, literally, there was things about not letting one user interfere with another user, but fundamentally, that was all hinged on this idea that you controlled where the code came from that a user ran. Because that was always the problem, that some user says, oh, run this cute game, and then they like bridge that security boundary and you ran that game and they did something like, you know, put up some silly message on your screen or something. But now we live in a world where essentially all of us run programs, run code that just shows up on our computer in random ways. What's the most common way that code shows up on your computer, gets executed on your computer? Code that you don't have any control over, really. Yeah, JavaScript, stuff off the browser. You go out on the web, you click on something, somebody's running a program on your computer as you. So the security models are kind of busted because the security models were all how to keep two users from interfering with one another. And you're like the guy, you're the person with the infection, you're the one who goes click and run it. How about all these mail problems, right? This is where you go get these mail messages and you click it and it turns out that JPEG image exploits some bug in some software. It's a very complex, unsafe world. And so the security models haven't really kept up. What do people do with computers? Well, not here, but what do people, you know, who buy all the massive computers, not just the people who use all the electricity in Europe, but the people who actually, you know, buy all the computers and make money for companies like Microsoft. What do they do with those computers? What do you guys do with computers when you're not at work? Anybody do social networking? I'd have somebody explaining what social networking was. Anybody here do social networking? Yeah, okay. How many of you do stuff that's like really media rich? Play music, play videos. How about games? How about doing physics at home? Okay, that's called games. Okay, there's a lot of stuff that kind of shows up in computers. It's not the same workloads, it's not the same kind of models we had before. So, and also there's all this stuff about your smartphone versus your laptop, your netbook, your television becoming a computer. Changing environment, opportunities for new operating systems. So I'm going to tell you several parts of this talk. That's one part. Operating systems are great. If you're not planning on doing stuff with operating systems, then either you have a life or you should do this until you get one. You know, start playing with operating systems. It's great stuff. So I'll tell you a little bit about the Windows architecture. We'll talk a little bit about how it differs from UNIX and about some of the more recent changes. This is some big fancy architectural picture. Let's see, I can do this several ways. Is that like showing up on the screen, right? So I'm not going to go into this picture because really the only part I really care about is the stuff all down here. So we'll go to the next picture because I work in kernel land. And so I'll tell you just a little bit about some of the differences here with UNIX. UNIX was one of these things, and even Linux is this way too, which was how do I quickly get from point A to point B in an environment where I'm so resource constrained, very small amounts of memory, very big limitations in the hardware, that the original design in Unix really lent itself to a very lean, clean kind of design where the stuff that in the kernel level you try and have a very few very simple things that you do. You don't build for any kind of generality. And all that generality that comes ultimately came later as it got added in user mode. What Unix did have was a great composition model, which my wife never appreciated, but the composition model in Unix that's so powerful is what? It's the Unix pipeline. This is an incredibly powerful composition model, which none of us actually use anymore, really. When's the last time you guys wrote a whole bunch of small applets to tie together with pipelines to do something? Okay? Well, yeah, but that's hardly counting. That's not the same as like when I was writing accounting systems in the computer science department to, you know, take the account file and figure out how much different students were spending on the computer. Well, I use grep and awk and all these things. And today most people do that with Perl or Python or some other scripting language. And most of the large applications that get written are composed, they're API compositions, they're not really pipeline-based compositions. Why was pipeline composition so important when Unix was born? Because you had 16 bits of address space. You couldn't write big, single, large applications. And we've never actually gotten a really good composition model back today. API composition has a whole bunch of problems with it. And so there are things that Unix achieved that we haven't really gotten back to. But this lean kind of approach that takes place in Unix was particularly true in the kernel in terms of how like file descriptors worked or kernel facilities. And these are things that never really got fixed. One of the problems with fundamental design decisions is it's actually very hard to substitute a completely different fundamental design decision. You can incrementally change things. So if you go from the Unix file system model that it originally had to the virtual file system model, how was that done in Unix? An incremental change. You said, well, we had this kind of character device switch kind of stuff. Why don't we produce a virtual device switch? And then we'll just plug in a file system. So it's like a pluggable file system kind of model. And we'll have like a set of entry points. So it's more like a dispatch table, which we learned from CDev switch and block dev switch. And then the problem is we had to fix a bunch of stuff that was on the wrong side of the abstraction. So a whole bunch of metadata operations had to move to a different part in the system. So things like make directory. Make directory originally in Unix was a set UID program. By the way, that's another reason fork is broken, is you couldn't actually fork very large programs, which you had to do if you wanted to create a directory because it required you to run a set UID program back in those days. And so that had to go into not only into the operating system, but ultimately had to be remotable on the other side of the file system interface. And so you find that you do things like this. So in the NT model, we actually had a very different approach because we didn't have those kinds of constraints. And so we tried to build general purpose architectural facilities that we could then reuse in various ways in the system. So our concept of an operating system abstraction is far more general. We have these data structures, we call them objects, but they're not object-oriented objects, they're just things. And we let you abstract everything like that, like a process or a thread or a semaphore, and they all fit in the same unified model. The way that naming works is the same kind of idea. So it's a very different approach at a very different time. And one of the things we were able to do, being less resource constrained, is the operating system itself is split out like you see in this diagram. That the kernel of the kernel is this thing actually ironically called the kernel layer, which abstracts the CPU. So what does it mean to abstract a CPU in operating systems today? Well, ignore Unix for a minute. It means to create a thread. It's like in Solaris or in Mac OS or Mac OS. It's funny how that worked out. Mac OS became Mac OS. It's that you want to abstract it as a thread. Okay, that's how you abstract the CPU. So the INTOS kernel layer builds up the thread paradigm. It also handles non-thread access to the CPU, like how traps, like you take a system call trap or you take an IO interrupt, how that gets mapped into running code. That all goes into this INTOS kernel layer. And so what that means, there we go. What that means is that all the rest of this code that goes in what we call the executive layer of the thing you boot that's called the kernel is actually written in a multi-threaded kind of environment, like you'd kind of write in user mode. You have multiple threads, they have synchronization primitives, you sometimes for performance have to worry about how to lock memory and things like that. Paging is a little bit more complicated because you can't actually page the paging path very effectively because you deadlock. But it's pretty much a fairly general environment. Virtual memory is fully supported there. You're running threads or running synchronization much like you'd write at user mode. So this is something that Windows did, and I think largely it did this because of when it was written. If you now look at some of the research, even stuff going on in Microsoft research, people start looking at could you implement an operating system with a microkernel and a runtime and do something like with .NET style managed code to actually write the operating system. And that's the Singularity project. You can actually download the code and see what they did with that. So there are other interesting things to do in operating systems. When I do my university talks, the basic message is that if people in operating systems courses are just saying Unix, this is it, this is what an operating system looks like. It sounds kind of really funny, right? Because you're talking about something that was invented, years before computer science really became a mainstream discipline. And for something that's so high tech, we're talking about a whole set of design ideas that got established in like 1969. And even if you go look at a thoroughly modern system like Windows, give me a break, that's like 1989, that's a long time ago. There's a lot of new work to do. There's a lot of interesting things to do in terms of how we think about operating systems. The most interesting operating systems work today, I would say, is going on with virtualization. People doing virtualization work. It's going on with people doing programming language runtimes who are taking over more scheduling, as we'll see. And it has to do with just synchronizing my watch with that clock. It has, yeah, I'm going to go by this because I think this is, well, that's the US. I was on an airplane. I pushed the button. It says, go to Colorado, go to NIST, set my watch, and then it'll work fine. And with the runtimes, the parallel language, with things like that, even database guys are doing a lot, well, they've always done a lot of operating system level complexity, like SQL. Microsoft SQL has what we call SQL OS. It fundamentally builds up a set of abstractions, kind of like the KE layer in the kernel, that then the rest of SQL is built on. So this kind of model is fairly common, but a lot of operating system work is going into those parts of the system. So I already described this kernel executive layer split. To show you more about the generality versus Unix, and I'm not saying there's something bad about Unix, I'm just saying different era, different set of problems. Most interesting question is blank piece of paper today, what it would look like. But in NT, because we have this general concept of what an abstraction is in the kernel, you get APIs that say, oh, give me back a handle. So it's like a file descriptor in Unix, except that you use these handles to refer to any kind of object from user mode in the kernel. You establish a connection with a handle, and now you can say, signal this semaphore. You know, do my P operation on this. You know, go signal this event. Do wait on this. Do stuff with file completion, because it's also a file descriptor. You can use it to refer to processes. In Unix, if you want to wait for a process to die, you can just take the PID and stick it in the select statement and wait for the process to die, right? No, of course not. You have a completely separate API, wait or wait3 as it's normally used, because it was like separate compartmentalized kinds of functionality, but because NT was built 32-bit address space, it was able to try and build more unified things. So actually a single call can say wait for something to happen, where something to happen can include file IO completed, thread died, process died, semaphore got released. You know, all these kinds of things can all be built into a single kind of paradigm. And it's just really a difference in when the systems were designed, what the hardware environments were that these operating systems were built. So some of the facilities you get are things like you can create a process, fine, you get back a handle in that process. You can duplicate that handle into other, not just, you know, within your file table like in Unix. Unix has a lot of operations that mostly involve being sure that 0, 1, and 2 are well known. You know what this thing is called, by the way, where you actually try and be sure that your files are connected at specific numbers? That wasn't actually invented by Unix. That was actually an IBM job control language in the 60s. You see it in Fortran. How many of you still ever read Fortran code? Right? Good. The unit numbers, you know, there were 5 and 6. The big innovation in Unix was to make 5, it became 5 and 6 over time, become 0 and 1, and then adding 2. And the original Bourne shell in Unix, which was the original shell in Unix, had this idea that you'd use these just like unit numbers on the IBM systems, where you could say, oh, here's file descriptor 6 pointed at this file, point file descriptor 9 at this file. Any of you ever done that? No, because it turned out that 0, 1, and 2 was kind of simpler, pipelines worked with it, and so we kind of lived with that model. The more general JCL kind of model kind of fell by the wayside. But we actually allow you to duplicate these handles across processes. So you actually have a different way of giving somebody access to an object, perhaps that you're sharing, than giving it a name and making them share the name. So I can actually take these objects like a handle on a process, and the second API here, I think I like doing this better, let's see, like red. Create a thread in an arbitrary process if I have the rights on the handle for the process. And I could have gotten that handle because somebody could have duplicated it to me. I can allocate virtual memory in a different process if I have the rights. I can map that memory, because our mapping model is more sophisticated than Unix is, because Unix's view of virtual memory isn't the pretty sophisticated one you find in Mach that you'd find in Mac OS. It was a very limited one due to the first virtual memory implementation being on the VAX computer I love. VAX actually had very limited virtual memory hardware, and that led to mmap working the way it does, for example. But we have a more general kind of model being designed years later in NT that allows you to allocate virtual memory in a different process, and then separately from allocating virtual memory, you can actually decide how to map memory back to objects, like shared sections, into your address space, and you can control that a lot more in NT. So these are just some of the things that give you kind of a flavor. Operating systems evolve along the same lines because hardware evolves, but they start from different design points, and those design points are largely determined by what the problems were and the environment that they were in. So that's like, I think, the end of part 2 of my talk. And now, I think there's 4 parts to this talk, so here's part 3. So I'll tell you about how little work, the little tiny amount of work we're doing this day in the kernel, so I hope you're not completely disappointed in this. When we normally give our talks, like Mark Rusinovich has a bunch of slides. I've given his slide deck on. He tends to write these slide decks and all the changes in the kernel, except it's always the kernel plus a whole bunch of other areas. Like one of the coolest features that came into Vista, is now a lot more usable for some practical reasons in Windows 7, is BitLocker. How many of you know what BitLocker is? BitLocker is how you solve all the fear in the United States, at least, about identity theft. Do you guys have that problem in Europe? Do you have a problem where like somebody loses something with all this personal identifying numbers and like your credit cards or your ID numbers and stuff because they leave their computer somewhere or somebody steals their computer? And now all of a sudden all that personal information can now be exploited to steal identities. Happens in the US all the time. BitLocker actually encrypts your hard disk. It just keeps all the stuff away, depending on how sophisticated you're being. It's pretty hard to crack, at least until somebody decides how to factor large numbers efficiently. It's pretty safe. And you can use the hardware level keys. You can stick in some kind of USB dongle. You type password. You can add all 3 levels of protection and pretty much have nobody who steals your laptop being able to get at your data. Okay, so that's a pretty important feature. How much of that involves the kernel itself? None. How much of it involves kernel mode? Sure, there's some drivers. But some of the more interesting work we do is actually enabling very important scenarios for customers. And so we still do some of that in the kernel, but we also just clean things up. So here are the big changes in Vista that actually specifically affect the kernel. Any of you know how traditionally CPU time is accounted on computer systems? Anybody know, like Unix used to do this, probably might still do it. We used to do it until this release. It's statistical. The timer interrupt fires, and in the timer routine, you can say, what was I just doing? And you say, oh, I was in user mode, or I was in kernel mode. Or I was switched to this process. I'm in the context of this process, which in Unix was what mattered. Or in NT, I'm in the context of this thread. This was the thread that was running when the interrupt occurred. And so you make the assumption that the entire time since you took the last interrupt was spent doing what you're doing right now. Okay? And you go write it down. So it's statistical. It's kind of variable. It leads to scheduling anomalies like we gave you a quantum, a scheduling quantum, so you get to run for this length of time, and then some big, long-running ISR occurs, some interrupt occurs, and you lose the CPU to the interrupt routine. We still count it for you. The interrupt routine returns, timer fires. We say, time's up. We're giving the CPU to somebody else. You're like, wait. I didn't get anything done. The guy came in and took all the CPU cycles. So that's what we do by using the timestamp counter now, which is now ubiquitous on the hardware Intel and AMD, so that we actually go look at and say, well, how long were you actually running? Because we know at the time the interrupt occurs or we do the context switch, we can go look and take a measure with a timestamp counter of when it was and just stopwatch you and get far more accurate scheduling. So that was one of the things that we did. We did some IPC kinds of things. I built a new TCP IP stack, so even I'm sneaking stuff in that's not in the kernel itself. It's actually in the TCP IP driver. Built a whole new stack that supports IPv6. Previously, all we had was a separate research IPv6 stack. We removed a context switch from I/O completion ports. How many of you know what I/O completion ports are? There's this problem with thread-based programming, which is when you go do something asynchronous, like an I/O operation, who are you going to tell when you're done? How are you going to report that the I/O completed if it's an asynchronous I/O operation, which all the I/O in NT is inherently asynchronous. Why is all the I/O inherently asynchronous in NT, but asynchronous I/O is kind of a rare thing to find in Unix? Because Unix was designed in 1969 for a very different environment than NT was designed for in 1989. It all comes down to those kinds of decisions. So in 1989, looking at server performance, you knew that asynchronous I/O was really very important. And so it has asynchronous I/O. And I/O completion ports are a way that you can initiate I/O off one set of threads and then do the I/O completions on a different set of threads. That's all I/O completion ports are. They actually tend to be really useful. Stellaris, I think, adopted them too. We removed one of the context switches from how those work. It gets you like 5 to 10% of performance, something like that in SQL benchmarks. And that's the level at which we've been making kernel changes for quite a while now. It's all very incremental kind of work. Address space randomization is just kind of cool. It was an idea I really pushed back in XPSP2, and we couldn't do it. And then the guy who owns the memory manager kind of figured out how to actually do it right in Vista. You know, when somebody finds a buffer overrun, they find some flaw in some driver or in Windows itself or some service, and they take over your machine, well, the way they really take over your machine is they basically, in general, there are other variations of this, but they're going to try and get a little bit of control over your program counter by overriding it in the stack, by overriding a V table in the heap. You know, usually it's because of bad parameter validation. It's the easiest thing you're looking for. How do you find vulnerabilities in an operating system? Any of you guys know how to do that? Any of you guys want to admit this to your peers that you know how to do this? You go figure out how to crash something. Particularly try and figure out how to crash it remotely. But if you crash it locally, sometimes that's good too. It's not as interesting. Because if you can crash it, then you know something's broken. And if something's broken, then you figure out how to exploit it. And every time we've had somebody at Microsoft say, it seems like every time, nobody will ever exploit that. Somebody figures out how. So every time you have like the least bug, because the problem in programming, particularly in this kind of software, it's not getting your program to do what you expect. It's being sure your program never does anything you weren't expecting, which pretty much taking an exception because you used a bad address, you weren't really planning on that. So you find one of those, and then you say, can I turn that into a way to modify something that lets me get control of the program counter? And then once I have control of the program counter, I'm going to try and modify it. Maybe I can only modify it slightly. Maybe I can only change a byte of it. You know, I want to modify it so it points at some instruction. And then I have a sequence of instructions and now executing those, and I chose those out of the code that was in the process already so that I could do something else, and eventually I can dump into my buffer, and eventually I can start to do all this stuff. The simple just jump into my buffer stuff doesn't usually work so much anymore, but even that was kind of hard. So what address-based randomization does is it says that we will lay out the libraries and the stacks on your system differently. And you'll have like maybe a couple hundred different possibilities or so. So that means that most of the time when somebody's trying to, they've worked out their exploitation, they can't find your code. They can't find the code they want because they don't know what state your system is in. And so they go change the program counter and they execute some random piece of code. And you just fall over. So you change these escalation attacks into denial of service, which if you understand virus epidemiology means that the spread of the stuff is much slowed, it's much easier to combat. So that was another change. Windows 7, we did this thing called MinWin, and my boss at the time, who was this guy who was really big in virtualization, he went off to University of Illinois and he gave a talk at this conference they had, and he talked about this thing called MinWin. And it was just funny watching what happened because a whole bunch of people got all these wrong ideas about MinWin. So hopefully I won't create that today. We talk about MinWin because we're changing how we're building Windows internally, not because we're changing what Windows is particularly. And the idea of MinWin makes sense if you know how Windows is built today. Windows is a fairly large monolithic bunch of code that we kind of can all compile. It's not so big that you can't like compile it on the machine in your office. We've always sort of been able to do that, you know, for 9, 10 years now. And so you just like build the whole thing together, which means it becomes really easy for people to do things that aren't so great, like take dependencies on pieces of code way over here simply because they can change that, change this, change the other thing, and then rebuild the whole system. And so we started doing a lot of work to make that much different. And so we're building Windows in pieces now. MinWin's this first piece where we say, okay, we want to build the core part of the system, something we can boot and test. It's got the kernel, it's got network device drivers, it talks to this, it's got the file system, and that's what we're calling MinWin. And that's actually turned out not to be so useful, so we're building a larger part called core system. And then we want to build Windows Server. We add a lot more code and functionality on, or we build Windows Client. We build it up from this thing. So we have this thing called MinWin, and Windows 7 is the first release of Windows that we built out of this new approach. We changed some things about working set management. Working set management is actually very expensive. We have a working set kind of algorithm in Windows. Working set means that you expect the working set model to hold, that you have a set of locality in the execution of a process. And we do it in processes, so it's the amalgamation of all the threads in the process. And you say that when you run out of memory in your working set size, we're going to like take the page away from you rather than from somebody else. So it's a way of kind of partitioning memory among applications. And it's different than like the clock algorithms that UNIX uses, which kind of says we treat memory as one big thing and we kind of take it from the big thing rather than from individual processes. And the reasons why they did that have a lot to do with how the backs worked. And one of the problems with working set or with any kind of virtual memory management is it's very expensive to collect reference bits. You guys know what reference bits are? These are the bits that when you actually go access a page, there are a couple bits the hardware generally holds on to. One's called the modify bit, because if you don't modify a page, we don't have to write it out to disk before we reuse it. We just get it off disk again next time. But if it's modified, we better write it out to disk before we reuse it. And an access bit or reference bit says that you actually use the page. Well, the working set idea, if you go back to Denning's paper, this is like 1969, 1970, was that of all the pages you have in your address space, you're probably using a fairly small set of them at any given time. And the algorithm that we largely use in working sets is something called least recently used, which means the pages that we replace, the pages you're actually now using, the new pages you need, we try and replace the pages you haven't used in the longest time. That's why it's called least recently used replacement algorithm. To get least recently used, you have to know whether or not, since you last looked, a page has been referenced. And that's why you have to go look at the reference bits. Well, it turns out this can be kind of expensive, so in general, we haven't been reading the reference bits all the time. We only do it when we start to run out of memory. The reason it's expensive is because the way the hardware holds on to the reference bits, it takes a fairly expensive operation to actually get an accurate representation of the reference bits. Okay, so that's a little bit technical. But one of the things that we did in Windows 7 was to stop looking at the global memory state before we start turning on the reference bit collection and start holding processes to live within their own reference, their working sets. Because what happens, and I think this got worse in Vista, is that one application starts to leak memory, starts to run away, starts to have excessive memory use. It basically can swallow all the memory because until the memory gets low, we don't start saying, oh, we got to start taking pages away. And so when we get to that point and we start taking pages away, and that might happen because you're running some application, something else sucked all the memory, and then you start a new application, and now we have to find pages for that application in order to run it. So this is one of the reasons I think you'll find that Windows 7 is a lot snappier than Vista was, is because we do a lot better management of the working sets. So the last two things I want to talk about are actually the things I think are interesting in Windows 7, and then we'll talk some about futures. These are interesting because they're interesting to me. I won't judge what's interesting to you, but you can give me some idea by your questions. So there's this core parking idea we use on servers, and I put this in because Mark Rusinovich did this animation. I was so impressed he could do this, I thought I would do it. So the idea of core parking is we care a lot about energy efficiency, particularly on laptops, but also on servers that we're not using the core. And so see how the animation does. We take these threads, we move them over to different cores, and we turn the core off. Okay, and this works if it's a different socket or it's some unit that we can actually power off on the system. So it used to be that scheduling was all about how do we get the most throughput through a system by spreading it, spread threads out a lot in case that they needed the CPU. You didn't want to have two threads trying to be on the same CPU because then they'd have to switch and the cost of moving them was expensive, so we tend to spread threads out. That's not very energy efficient because if you don't have enough threads to keep them busy, you'd like to turn them off, and so we started building some logic to do that. I think he's going to turn them back on. This reminds me of like playing Go or something. There we go. That's Mark's animation. This one I like better. Energy efficiency also has to do with the fact that operating systems are driven by events. There's a lot of housekeeping that takes place. A lot of applications get written. Like these are interactive applications. Do things like every hour, wake me up so I can go do something. Every 10 minutes, wake me up. Every 30 seconds, I need to run a thread just to check something. And so they have these timers. A lot of timers go off. And if you're trying to get energy efficiency in the machine, the timers keep waking up the CPU you were trying to put to sleep because they run out of. Ignore core parking for a minute and just talk about a situation where you have no threads to run at all. It means you can turn off the CPU by lowering down, it's putting it in a halt mode, which is a very efficient, energy efficient state on most modern CPUs. But then the timer fires. And now you have to spin the whole thing up again and then shut it down. So we did something called timer coalescing. So you can guess what this is going to look like. Because it turns out that most of those applications don't really mean precisely exactly an hour from now. They mean kind of roughly an hour from now. So we said, well, start telling us how much flexibility you have, and then we'll just kind of coalesce these timer events together. So when we wake up the CPU, we fire all the ones that are in the vicinity Because I think it was kind of a programming mistake. It was a design mistake to have APIs that said, here's exactly to the millisecond when you want to fire this timer, when you don't really care. So we did some stuff like that. Now this guy, really bright young guy, Arun Krishnan, who has master's at Stanford, came to work for me. Everybody likes to be Arun's buddy now because he did something that was really delightful. When we run large SQL applications, particularly as we start looking beyond 64 logical threads on the machines, the hot lock is in the scheduler. And Arun took it on himself to go, so he's been there like, 7, 8 years now, so he's actually more of an old timer, I suppose, but to break apart this really hot lock. So this is like, if you're a kernel guy, this is like one of those real kind of geeky kinds of things you really love. But this one particularly had lots of very positive implications because the scalability for running large server code dramatically increased. We could now go from 64 to 128 logical threads with something like a 1.7 speed up on the SQL benchmarks we were using. Okay, so it's actually fairly impressive work breaking up the lock. So I won't go into the technical issues. And then we also took out another lock that wasn't quite as hot. So I then want to talk to you about something I worked on called user mode scheduling. So you remember that I said how processes became threads as the hardware changed. Now that we're going to get more cores, maybe we'll get more of a task-based model, which we're seeing today in things like ConcRT, which do over-decomposition of programs into tasks and then schedule those tasks onto threads. Part of the reason you do that, by the way, is creating and destroying threads is a relatively expensive operation. And so you use thread pools for a long time. We try and amortize that. But it turns out that in these parallel environments like ConcRT is building, you actually want to deal with real physical CPUs. You want somebody to give you a physical CPU, not a simulation, a virtualized CPU. In other words, not a thread. And so we built this user mode scheduling, so it's a bit like scheduler activations. But it's actually a little bit more interesting than that. So if you take a look at what a thread is today in an operating system, you guys all think you know what a thread is, right? You got to create a thread, it's a thread. Well, no, it's not. It's actually two threads. It's a user mode thread that has its own stack, its own place it saves registers and stuff, and it's a kernel mode thread. And these things are implicitly tied together, so you thought they were one thread. So when you go from the user thread, or I call the UT in these diagrams, to the KT, we do an implicit context switch as you enter kernel mode to switch to the stack for the kernel thread that's associated with your user thread. They really are two threads. And once you realize this, then you can go from this existing kind of NT threading model into one where you can have user mode schedulers switching between the user threads. And then it's only when you enter the kernel that you say, oh, now I got to do that context switch to get the right kernel thread running. But now instead of being an implicit switch, it's a little bit more explicit because you could have any of the user threads running when you enter the kernel. And now you have to go pick the right kernel thread to run. And the only other real idea, I guess there are two other ideas in here. So that's the main idea. User mode scheduling enabled because you defer the kernel mode switch and make it explicit instead of implicit. And the other two things is now that I'm in kernel mode on the same CPU, if I block because I would have to wait for disk or I have to wait for some semaphore or something, you want to give the CPU back to the user mode scheduler so it can schedule something else. Do you guys know what gang scheduling is? Everybody knows what gang scheduling is? It's where you have a bunch of CPUs and you say, I'm going to come and make these in lockstep. I'm going to assign these 4 CPUs at once. And that's kind of convenient for certain kinds of programming models because it says that you can share data using very fine-grained locks, which is what the operating system generally does when it uses spin locks. It can say, I can use a very cheap lock to synchronize between 2 different CPUs if I use gang scheduling. If you don't use gang scheduling, it's just dicey because if the lock is very contended, there's a danger that who's ever holding the lock might block in the kernel, they might take a page fault, something bad might happen, and now you can be a little bit stuck because you're holding this lock and you don't get control back, so you can't really fix it. So gang scheduling is an interesting area, which unless you have this kind of mechanism for returning the CPU, is not very useful. gang scheduling has a very bad reputation because the CPU utilization becomes very poor because all the threads block in the kernel. Nothing's now running on that CPU. So in this model, what we're doing is by returning the CPU back into the scheduler once you block, we give the user mode scheduler the opportunity to release the lock, perhaps, or to just run some other thread that's ready to run. And then the other change is that when you eventually complete your system service and unblock, there needs to be some kind of completion list that the scheduler uses to say, oh, I know what user threads are now runnable again because I got the message off the queue that says that that kernel thread completed the kernel operation, the page fault, and now the user thread is runnable. So this is user mode scheduling. Oh, and I got another animation from Mark. So thread scheduling looks like this. User mode scheduling, we broke the threads into the UTs, the user threads, and the kernel threads. And now up in the user mode scheduler, you can sit and play with user threads all you want until eventually, I guess he's pretty thorough here, you enter the kernel, and then you do this explicit kernel switch. So do you guys like Mark's animations? Okay. The tech audience is like in the more commercial space where he goes and gives these talks. They love his animations. I'll have to watch him more carefully and see how he's doing that. All right, so there's some other history which I think I'll ignore. And now I'll go to the last portion of the talk before we take questions and talk about, try and connect this all together in the following way. Hardware environment continues to evolve. I've made that point several times. What kind of operating system, if we had a blank piece of paper, what fundamental changes in how we think about computing might we be looking for in the future? And so now I'm going to do some speculation about that. The one thing I want to be really clear on, just because of the nature of where I work and what I do, is that what I'm going to talk to you about are not any kind of specific product plans that Microsoft has. The irony being that if they were, I couldn't really discuss them. But because these aren't related to any specific product plans, I can talk about them all I want. Okay, so don't take this as this is what's going to be in Windows 8, because it's probably none of the stuff would make it into Windows 8. We're too far down that road. But if I prevail on some of my ideas, if these turn out to be the right kinds of ideas, maybe you'd see these in Windows 9 or Windows 10 or something like that. So this is that UMS kind of model I showed you before that's in Windows 7 today. Except I did two things, but the first thing I'll show you is I made the system call queue also, the system call request also be a queue rather than an actual trap into the kernel like it is. So let me tell you why that's kind of a very interesting thing to do. It's very expensive to cross rings into the kernel, and maybe that's fixable. Right now there's just a lot of machinery that takes place because of the generality of the x86 that's just expensive to cross into the kernel. A second thing is it's expensive for indirect reasons because you end up having essentially two CPUs or two activities that are sharing the same CPU and the same cache and the same physical resources, and effectively they can interfere with one another by evicting each other's cache lines, for example. So you go from user into kernel, kernel does a bunch of stuff, goes back to user, and the user now has to sit there reloading his cache lines because the kernel kicked out some big chunk of them. So there's some interesting efficiency problems with that. If you allow system call queuing, you can go through your program and say, okay, here's like the 8 things I think I'm going to do in the kernel, batch them all up, and at some point finally take the cost of going in the kernel. The kernel goes through and does the 8 things or maybe the 6 things until one of them hits an error, in which case it returns and lets you deal with it. And I can amortize the ring crossing and the cache poisoning that takes place. That's the first thing I can do if I go down this road. The other thing is that you can remote the system calls. Because there's no reason that queue necessarily has to be on the same CPU that user mode code is executing. Now, where that gets to be interesting, and one of the things I've been thinking about lately, is what happens when we get all these multiple cores, this mini-core kind of phenomenon where we're trying to figure out what happens in the universe of computing now that we've hit the power wall. We'll talk more about the power wall in a moment. We're going to get a lot more transistors because Moore's law is still valid, but we're not going to get faster clock rates. You guys all know why, right? Because power consumption, it's called a power wall because power consumption, power dissipation goes up as the square of the clock rate. And fortunately, It also goes down as the square of the voltage. But we're now at the point where the voltage isn't going any lower as we're playing a few games that remain, but clock rates aren't going to go up. Instead, we're going to get more cores, more CPUs express itself. One of the ways those transistors might express themselves as CPUs is to have non-x86 specialized cores. Remember array processors or attached processors, or the poster child today is GPUs. Any of you doing GPU coding? You're writing stuff for GPUs today? And so we could see a lot more of that where we get past GPUs and start trying to build general purpose accelerators for computation, in which case we really don't want to run the kernel on the same core that we're running the user mode code. We want to use this model right here to be able to remote the work to an x86 which is able to run the kernel and do the service. You also have issues with kernel scalability. If we're going to make use of all these cores, all this computational ability we're getting, we better not have the same requirements on the system part, the system component of the computation, because system computation tends to be fairly serial compared to the parallel computations we're looking to do in the future. And so you don't necessarily want to be trying to scale your operating system if you have 100 cores to try and run the operating system on every single core. You might run it on 20 or 30, and anybody else would remote their system call request, and you choose the number of cores the operating system on to give you the right kind of throughput. And this is this master-slave, which, like gang scheduling, has had utilization problems in the past, because with master-slave you would give up, you'd wait for the operating system core, you would get nothing else done. But with user mode scheduling, because we return the CPU back to you, you continue running other threads while you're waiting for the system service to occur, which isn't all that much different than what happens when you block in the kernel today and switch to a different thread. So these are interesting possibilities for innovation in operating systems that I think are coming in the future. So this many-core challenge is really very, very big irony here. For a long time, there's been a lot of discussion for, I don't know, 30 years, my entire professional life, about when Moore's law was going to end, right? Doesn't the law of physics take over and stop this? Moore's law is the number of transistors, the feature size actually halves every more than 18 months. In practice, it's like it turns into the number of transistors double every 22 to 24 months. This is like on Intel's curves. And that's been Moore's law, and that has continued to be true somehow pretty much, since the 70s. And the interesting part is that Moore's law is going to become irrelevant before it's wrong, it seems. Because Amdahl's law, everybody knows what Amdahl's law, who works in computers here, I'm pretty sure, right? Amdahl's law is going to become dominant. Our ability to write software that can take advantage of these processors is going to limit what we can do computationally. Because it turns out that we haven't exactly been writing Moore's law. We've been writing, in general purpose computation at least, we've been writing clock rates. This is actually what RISC was all about, was increasing clock rates. We've been writing clock rates, and clock rates are like a rising tide lifting all boats. All parts of the program generally got faster. With parallel computation becoming the rising tide now, and all your serial computations not getting faster because the clock rates aren't getting faster, Amdahl's law becomes a dominant. So I guess that was my signal to finish. So a couple more things. This is my last slide, so we are close. If we start scaling the OS, we might move toward this thing I call shrink wrap on the bottom line. And there's another idea I have called freeze dry, which is shrink wrap is already sort of possible today. In virtualization, you can actually take your computation, right, download it onto this virtual hard disk format, and then resume it at some other point in time, and perhaps even migrate it between servers. This is a form of freeze drying. I think there's another form of freeze drying simply where most interesting applications that interact with human beings have quiescent points where they have very little state, and what you can do is just have the application say, here's how to restart me so I look exactly like I am right now at any time in the future you feel like restarting me. So you don't have to save my actual bits like you do in a VHD or in a checkpoint. You basically get the instructions to restart the program. Most of you who use Office have been seeing this freeze dry kind of technique applied for a long time. This is where Outlook says, gee, encountered a problem, mind if I tell Microsoft? That's probably the only reason we annoyed you, because all it's really going to do is it's going to restart the process, put everything back like you had it, with the intention you wouldn't really understand except for the minor disruption that they had encountered the problem. So we should stop asking for permission to tell Microsoft. You know why we want to know? Because our business is data-driven. Our decisions about what bugs we fix, about the kinds of problems we have, about the issues in the ecosystem, about what countries are being attacked by what piece of malware, about what vulnerability and what third-party application is allowing bot networks to be created. All this kind of information we're getting by that thing where you kind of say, okay, I'll let you tell Microsoft. We're actually taking samples off of tens and hundreds of millions of machines that we run through a large data analysis, mine this data, and we understand enough of what's going on in the ecosystem that we can issue patches, we can fix problems, we can even start to get information about how to find out what features people really want and where we should do our improvements. My favorite feature would be if every keyboard had the "this sucks" button, because I think we get better data than ever, because people don't generally tell you when something they expect to work well works well. They tell you when it's not working well. And if we had that, then we could go back and look at the trace and say, you know, we have a spike in people thinking that this experience sucks. What was the computer doing right before they started hitting the button? And that person always hits it 10 times, but that other person usually hits it only twice. Turns out we never get to know that because all this data is very anonymous. So you see in 2 reports, we generally don't know that much about where these reports come from. But there's a lot of possibility in collecting data, and so we do that. And so we started to apply this to freeze-drying applications. And that would mean things like you could shut down a whole session of Windows, but instead of having to save the entire operating system and all the bits, you go save a virtual hard disk and you bring it back, 3 months later, you have all those security patches to apply and reboot. So what was the point, really? Okay, it's more for server management than for using on your laptop. But we get to the point where you can freeze-dry applications and experiences. You can just sort of add CPU and memory to these experiences and move forward. And a similar kind of idea is turning applications into the unit at which we allocate resources in the machine. And so if you look at the relationships between hypervisor, kernel, and the runtimes that come with the programming languages, we'll call them the application runtimes here, the kernel's been like the center, literally, the name kernel, of the operating system universe for a very long time. My own personal prediction, which might be surprising given I work with kernels, but not surprising because my PhD research was about how to do this, actually, the kernels might go away. And what would happen to what's in kernels today is 2 things. There's 3 things in an operating system, roughly. There's a whole bunch of library code that shows up and the services related to it that let you do all sorts of things for code you don't want to write. That's just stuff that links into your program. That doesn't really matter so much. There's resource management. How do you decide who gets CPUs and memory and when, and how do we schedule things? That's in the operating system kernel today. And maybe there's 2 things, because I lumped the memory and the CPU together. The memory and the CPU scheduling is going to actually, the details of it will move into the runtimes, and that's what we're seeing with ConcRT and UMS, where the user mode scheduler is deciding who gets the CPU. And the allocation of what application gets how many CPU cycles over the next interval, who are we assigning CPUs to, who are we assigning physical memory to, is something that's already present in the hypervisor today. And so in essence, the functionality that's in the kernel today, some of it may move up into the hypervisor, and some of it may move down into the runtimes. And so then what a shrink-wrapped application is that you have an application or a set of applications that work together, you have an experience, and the libraries and services that you need to run that get bundled with it in terms of the private services you need. But any of the shared services are basically on your list of things you need to be provisioned. So you have an application. The application says, I need all this stuff to be able to run, but I also need to be able to access this shared disk. I need to be able to have this interface to this file system. I need to be able to get to this network service. And so a shrink-wrapped application is one that you basically take all that operating system functionality, pick only the stuff you need for your application, seal it all up into a unit that then gets wired into memory, CPU, and services, not by the kernel any longer, but by the hypervisor. And then where freeze-dry comes into it is you'd like these applications to be things that you could take them, put them on the shelf, restart them at any point, you get a far more consistent experience perhaps than you get today. So that's just some thinking in general about places that operating systems may go in the future. Thank you very much for your attention today.
Okay, thanks a lot again. I think that we have shorter session of FAQs as expected because we have, as you know, the presentation of 3:30 by the DG. Let's allow ourselves 5 minutes, but if you want to take longer questions or elaborate, we could just do it outside, just to allow the people to prepare the room for the next presentation, yeah? So any question? Any question that you want to make in public? No? Okay, I think that...
Okay, thank
so,
you again.
Let's thank again, yeah, Dave Probert. Sí,